Hi, we're wanting to evaluate this integral, this definite integral from -1 to 2 of this function, e to the negative x squared minus x dx. And so what this integral would represent, we would expect to get a number from this. Over here you see a graph. This is a graph of the function y equals e to the negative x squared minus x, graphed from x equals -1 to x equals 2. And so what we would get from this integral would be a signed area of this region between this function and the x-axis. And so you can see that the curve is below the x-axis on part of the graph. So we would expect to get a negative answer for that part of the integral. And the curve is above the x-axis for part of the graph. And so for part of that, we would expect to get a positive answer for that part of the integral. And then when we add them together, we would have some cancellation with some negative numbers and some positive numbers, but overall we would expect this answer to be positive. We have more positive part of the graph than we have negative part of the graph. So usually when we do a problem like this, we can either just use geometry to find the signed area of the region, although this is a curve, not a circle or a shape that you know area of, so that doesn't really apply here. Or we might find an antiderivative and use the fundamental theorem of calculus to find the value of this integral. The problem here is that e to the negative x squared is not a function that you're going to be able to write down an antiderivative of. So you may not feel super comfortable knowing that, or you might just think, well, I just don't know how to do it yet. But the farther you go in math, eventually you'll come to recognize ones like this, that this is actually a non-elementary integral, which means you can't write down a nice, concise function whose antiderivative is this. And so what we're going to talk about is how you might still be able to get an answer for this problem, even though you can't use basic geometry and you can't use fundamental theorem of calculus, because we can't write down an antiderivative of this function. So we're going to use some numerical approximation methods, and we're going to start with using rectangles, like we did at the very beginning when we used Riemann sums, and then we'll talk about using some other shapes as well. All right, so in order to do that, I'm going to need some coordinates of some points on this curve. So I'm going to pause the video for a second. I'm going to write down coordinates of some strategically chosen points on this curve and make a little table of values. And then we'll pick the video back up and finish what we're doing to numerically approximate this integral using the function that we have and the points that I'll write down. Okay, so I made a table of values. I just chose some x coordinates from -1 to 2, and I chose a couple of decimal places in between, halfway between -1 and 0, and halfway between 0 and 1, and halfway between 1 and 2. And I have approximations for the y values here from my function at each of those points. So those y values came from just using my function equation, y equals e to the negative x squared minus x. And I just used my calculator to get some decimal approximations for these y values. These are all approximate y values, not exact. The only one that's exact is the 2 here. So these are all approximate y values here. All right, but what we're going to do is use a numerical approximation. We're going to start with rectangles. And I've drawn some rectangles here. I've got 3 rectangles here. And we're basically just going to go back to that Riemann sum definition that we talked about and use a Riemann sum to approximate the value of this integral. So for this first approximation that I've got here, when I've got a picture drawn from, I've got 3 rectangles. And I made them all equal width. Remember that when we do a Riemann sum in the definition, you do not have to have equal width partition, but if we're going to do some calculations here, we can make things easy for ourselves and use equal width rectangles here. So I use 3 rectangles of equal width. And since my interval was from -1 to 2, so width 3, when I divide that into 3 pieces of equal width, each of these rectangles here has width 1. They all have width 1. All right, so we have width 1 on all of those. And we've got a point. I used a left endpoint at each of those subintervals. So at each of those subintervals, I used a left point, and you can see I put a dot on the function curve right here to get my height function. So for this first rectangle that I have here, I used x equals -1, and so the y value, the height of that rectangle, is 1.74. And then for my second rectangle, I also used the left endpoint of that subinterval. I used that to get the y coordinate of that function. And so that one is at x equals 0. That y value is 2 up there. And then for the third rectangle here, I also used the left endpoint of that subinterval. So for that one, I used x equals 1 as my x coordinate. And my y coordinate of that point is at 1 and approximately -0.26. Okay, so for this first approximation here, I'm just basically doing a Riemann sum, 3 rectangles of equal width. I'm going to form my products. Function output, 1.74, times the width, times the delta x, which would be 1. And I'm just going to multiply those. This represents the actual area of this first rectangle. And then the same for my second rectangle. Function output, or height, is 2, times width is 1. And then for the third rectangle, it's not actually area because I have a negative y value. It's assigned area. But we're just taking function output times width. All right, so for each of these things that I have here in this product, we've got a function output, f of c1, times a delta x1. All our delta x's are the same. F of c2 times delta x2. And f of c3 times delta x3. Right, so this is really just a Riemann sum. And so if I just do this calculation, do these multiplications, and do this addition, I get an approximation for this integral using 3 rectangles at equal width, and I use the left endpoint of each subinterval. Okay, so we do that calculation, we add that all up, and you should get approximately 3.48. Okay, so although this integral here is a non-elementary integral, which means I can't find an antiderivative, I can't use fundamental theorem of calculus to do that, I can go back to just the definition and think about that and get an approximation. So I got approximately 3.48. You should probably look at this picture and say, I don't think that's a great approximation. You're right, it's not a great approximation, so there are a couple of ways we can make this approximation better. One is I could use more rectangles, narrower rectangles. Another is that I could more strategically choose my points. So instead of perhaps choosing left endpoints, I might want to choose another point as the coordinate in each of those rectangles. So I'm just going to do another one with 3 rectangles for now. We'll maybe look at some with more rectangles or other shapes in a next video, but we'll do another one here with 3 rectangles. Again, we're going to use equal width rectangles. And this time, instead of using a left endpoint of each interval or a right endpoint of each interval, I'm actually going to use a midpoint of each interval. Midpoint of each interval. So in this first interval that goes from x equals -1 to x equals 0, I'm actually going to use the midpoint, or the point halfway between. At x equals -0.5, y is approximately 2.06. So we're going to get a rectangle that's going to be a little bit better approximation for that true area. And then on the next rectangle, I'm going to use the midpoint between x equals 0 and x equals 1. So I'm going to use x equals 0.5 for my x coordinate. The y value of that point is at about 1.06. So if we look on your curve here, right there, so this would be the rectangle for the next region. And you can see that that one goes a little bit above the curve on part of it, but a little bit below the curve on the other part, and it's probably going to give us a better approximation for the true area. And then for the third rectangle, again, I'm going to use another midpoint. I'm using midpoints of each subinterval here. So for this third rectangle, I'm going to use the point that's halfway between x equals 1 and x equals 2. So at x equals 1.5. And so we're going to have a y value down at about here. And so we're going to get a rectangle that looks about like this. And again, you can see that that rectangle doesn't fit the curve perfectly, but the part that is outside of the curve and the part that we missed that is inside the curve are more balanced than the rectangles we had before. All right, so we're basically going to do the same kind of thing. We're going to have a Riemann sum here. The difference is that our y values, instead of coming from the left endpoint, our y values, we're going to use these y values, which all come from the right endpoint. The other important thing to notice about this is that if you use the same width, all of our widths here were 1, so I didn't even really have to multiply by those. But if you use the same width for all of your rectangles, you can actually factor that width out. So I could write this as delta x, as long as I have the same delta x for all of them, times, and then just the sum of my endpoints here. So my f of c1, f of c2, and f of c3 for this approximation are going to be these three values I circled here. My delta x is 1. So my f of c1 will be my y coordinate at the left midpoint of that first left interval. So the y coordinate at negative 0.5, 2.06. And then my next y coordinate, 1.06. And then my next y coordinate, negative 1.29. And if I add all those up and multiply by 1, I get 1.83. Which is probably a better approximation for the value of this integral that we started with. If you look at the picture, you can see that those rectangles are a better approximation. And you can make more and more approximations. You can use other shapes. You can use more rectangles, a smaller and smaller partition. But the main idea here is that when the things that we've learned since we started talking about the definition don't apply, we can always go back to that definition. So this is a pretty good approximation. We'll look at some other approximations for this same region and see if we can get a little bit better approximation for that. But that one's actually pretty good for the value of this integral on this region.